Okay, so hello and good day, class. So we are going to discuss now the solutions of the worded problems you had in your quiz last time. So we're gonna just focus on the worded problems we had. I think we should go over with the solutions. So as we can see here for the first problem, this is a problem on the dead loads or the calculation of dead load. Of course, I have already pasted here the references or the tables needed for this problem. So anyway, this is a simple problem on a beam, a cinder type concrete beam wherein it is a 4-meter beam and it carries 1-meter height clay brick which is 12 inches in thickness. At the same time, it carries a ceiling with having a tributary area of 2 meters by 3 meters. So the kind of ceiling is asphalt shingles. So as we can see here, perhaps we will have a beam. Okay, so this is a beam carrying, first it carries here a distributed load caused by the wall, which is 1 meter height, and at the same time it has a ceiling load here beneath the beam in an asphalt shingle kind of ceiling. So first, perhaps we can have this dead load of the wall or the wall for the clay brick, and of course we have here the dead load for the ceiling or the ceiling load. So all we have to do is to look into the table. We look into the table here. So first we will proceed to the clay brick. So the clay brick in the table is on the walls. So it is actually 12 inches, which is 305 millimeter clay brick. We are in English unit, so we're gonna pick here 5.51 for the clay brick, and then for the ceiling we have here asphalt shingles, and obviously that is 0.1 here. So next, we're now going to the solution. So for the clay brick dead load of the wall, so this is equal to, perhaps this is familiar to you, kilonewton per square meters is already in the form of the pressure. So all we need is just to multiply this by the equivalent height, as we have learned in the earlier tutorial. So we have, from that we have to the pressure is to be multiplied by the equivalent height, right? So the equivalent height is already given. Okay, so P, or the pressure here, is equivalent to 5.51, and simply multiply that by 1. So 1. Therefore, this is equal to 5.51 kilonewton per meter. Okay, so 5.51 kilonewton per meter. So that is one of the requirement in your exam. We have 5.51 kilonewton per meter as the dead load of the wall. Next, so for the ceiling, dead load of the ceiling, okay, so as we can see, It is all in terms of kilonewton per square meter also. Again, this is the pressure multiplied by the tributary area, right? So the tributary area, or the area of coverage of that ceiling, and then this now becomes force, because this is P, or kilonewton per square meter, times square meter becomes kilonewton, or that is a unit for force. All we need here is just to divide this by the length involved here. Okay, so we know that the length is of course here for 4 meters, 4 meter length. So L is equal to 4 meters, and then we just substitute. So as for the pressure, that is equivalent to 0.1 kilonewton per square meter, okay, times the tributary area, and of course this is already given in the problem, 2 by 3. So meaning we just simply substitute. We have 2 by 3, okay, and then divided by the length of 4 meters. So we come up with the ceiling dead load equivalent to, we have 0.15 kilonewton per meter. So we have here now obtained the dead loads of the wall and the ceiling that is being carried by this concrete cinder. So it is also one of the unknown in the problem that we need to compute for its self-weight. So for the self-weight, let me erase this first. It, it had mentioned that the cross-section of the beam is a rectangular one. So I think that is 0.3 by 0.4. So we'll just get the unit weight of that one looking at table 1-2 of the ASCE 7-10. We can see here that the concrete plane cinder, or reinforced concrete cinder, is equivalent to how many? 17.4. So we're gonna use gamma is equal to 17.4 kilonewton per cubic meter. So from that, we can now determine the weight, because the weight is simply just equal to the gamma times the volume, and then we have here 17.4 times the volume. We just have length times width times height, or 0.3 by 0.4 times a 4 meter length. So this is the W, and then we will now get the distributed load by that self weight, or we have the small w here. So we all know that the distributed load is just simply the force all over the length where you wanted to distribute the weight. So from that, we have here the force. This one, we'll just have to adapt it here on the numerator. 17.4 by 0.3 by 0.4, okay, times 4 all over the length, and the length of the beam is equivalent to 4. So as we can see here, 4 is cancelled. So the distributed load by the self-weight is equivalent to 2.088 kilonewton per meter. Okay, so that's it for this problem. Okay, so may we now proceed to the live load problem. So here we have given a figure wherein it shows the framing system of a certain building carrying a lighthouse storage facility. So we are now required to determine the uniformly distributed load at grid C. So we're gonna focus our calculation at this portion, okay, at that portion, and then compute for the load that is carried by this grid C. So perhaps we can have here a shaded portion. So this is the tributary area actually that the grid C carries. Okay, so the grid C carries. So from that, the first unknown actually is the influence area. The influence area. And as we all know, we have the influence area to be equivalent to the KLL times the tributary area. So KLL here is the live load element factor, and AT here is the tributary area. So we can find the values of KLL through this table here for dash 2. So as we can see that the beam here is at the edge, although we do not have any extension or cantilever beam here or either way. So anyway, as we can see here, the factor would be edge columns with cantilever slab. So it has no cantilever slab. Edge beams without cantilever slab. So we have the same values there. So I think we're gonna adopt this edge beams without cantilever slab. So it is having a KLL value of 2, or live load element factor. So I'm gonna place that one. KLL here is equal to 2. And then for the tributary areas, we can see here that is 7 by 6. We just have that one, or 7 by 6 divided by 2. So in short, we have an influence area equivalent to 7 by 6, or 7 times 6, that is 42 square meter. So actually this influence area is the your criteria on the limitation of the reduction in or reducing live load. So we have discussed that one. Let us recall that criteria or the limitation of this reduction. We are just allowed to reduce a certain live load when we have an influence area greater than. So what is our restriction? So influence area should be greater than or equal to, we have 300 square foot, or that is equivalent to 37.2 square meter. So perhaps may we correct this one. This one should be 400. So our influence area should be equivalent to 400 feet squared, or that is equivalent to 37.2 square meter. So an area which is less than this value, whether 400 square foot or 37.2 square meter, then we cannot really reduce the live load. We cannot really reduce the live load. So another criteria is that the load should be less than. By the way, we have two variables of the loading here. We have LO as the unreduced live load, and L is the reduced live load, or just perhaps this LO is denoted as original live load, and this is the revised live load or reduced live load. So LO should be less than 4.79 kilonewton per square meter, or in English that is 100 pounds per square feet. So any load exceeding this one, then reduce we cannot reduce the live load. So those are the important restrictions. Not every load is subject to load or live load reduction. So these are the criteria in reducing or in implementing a load reduction. So going back to our problems, of course, for letter A, we have already obtained the influence area. And then for letter B, so I think the problem for letter B is, what is the uniformly distributed live load, or the L, for a storage warehouse facility, which is specified as light. So it is already here in the table, 6. That is 6 kilonewton per square meter. So we are asked to compute for the reduced live load if it is qualified to be reduced. But obviously, 6 here is already larger than what we have discussed as the limit. So it is already greater than 4.79 kilonewton per square meter, meaning we are not allowed to reduce that one. So therefore, our reduced live load is maintained to be L, equivalent to 6 kilonewton per square meter. So this is the answer. Okay, so that's it.